Hi, my name is Jim, and today we're going to do a little walkthrough in Multisim with AC circuits. And what we're going to do is build a simple two-element circuit. It's a high-pass filter and kind of move around using virtual instruments, which are located over here, and the grapher, which is pretty cool. We'll be setting that up under the simulation environment. So, this is a real quick review. This is my parts list here on the top, and I'm going to need a voltage source for my little circuit here, and I could use a function generator out of the virtual instruments, but it's easier, I think, to use an actual source. Now, the good news about using a virtual instrument is that it looks just like a function generator, and you press buttons and set knobs and so forth, so it gives you some experience with regard to that. So I'm going to select signal voltages, and my interest here is a sine wave. So AC voltage indicates one. I'll click this and set one of these in my workspace. And now I'm going to click on power sources, and well, what do you know? AC power has the same symbol. So what's the difference between power source and signal voltage source? And the answer is, in power source, you would set this voltage in RMS. In signal voltage sources, you'd set it in peak. Now, could I use power source? Sure. But to set this, what I'd have to do would be multiply its value by 1.414 to set it to the peak value. So, seeing that we have an actual signal voltage source which is in peak, let us use it. Next, I'm going to place a ground, actually two. And next, I need a couple of parts. So I'm going to close this out and then go over to this guy, our place basic, clicking him. I have a choice here. For example, I could certainly pick out this resistor, and if I do so, I have my values, and further, I have my footprint. So if I were going to lay out a circuit board, I would be wanting to use this resistor. Now we're not going to do that, so I'm going to select rated virtual, and there's a few advantages to that. One is that oops, what did I do here? There we go. One is that I can set the power rating, and if I make a mistake and I burn a resistor up, it's better that I burn it up in Multisim than I do in an actual circuit. So I'm going to go down here to resistor rated, select him, and there's my resistor symbol. And I'm going to put two of these on the worksheet. And next I'm going to get an inductor rated and put one on the worksheet. Then I'll close this. I have all the parts I need here. So before going on, notice that the scroll button on your mouse will increase and decrease the size of your worksheet. So if I'm going to want the voltage drop across this too, I kind of not comfortable with the way these are laying out, so I'm going to rotate this 90 degrees. It does not matter with an inductor. I'm going to rotate the resistor by 90 degrees. It does not matter. In certain parts it does matter, like for a diode, for example, it'd matter a whole lot, or an electrolytic capacitor also. It'd be very bad not to pay attention to polarity with those guys. Next, I got to set my values. So for the inductor, and this circuit was worked out in advance, so I'm going to make this 10 millihenries. And notice below it I have coil resistance. Well, this circuit calls for a coil resistance of 50 ohms, and I could certainly set it here, and it would work just fine. However, somebody looking at this, not seeing that the coil resistance is an explicit part of the circuit, unless they open the window, might not take it into consideration, and that's going to be part of the total resistive component of the impedance of the circuit. So my other option is to put a resistor in series and let it be the winding resistance. I'll use option 2 on this. So this will be my winding resistance, and it's going to have a value of 50 ohms. So under value here, I'm going to set this for 50 ohms. And note that the power dissipation of this is a quarter watt. If I exceed this, the resistor will burn open. So I'm good with that. And the other thing I have to do while I'm here is change the label. R2 doesn't mean a whole lot as a reference designation. So I'm going to rename it RW for R winding. That'll make it a little bit more explicit. R1 is perfectly fine with this, but the circuit values call for this to have a value of 450 ohms. Set that. And now for the source here, I need 10 volts. There's my guy. At 5 kilohertz, there's this guy. And I'm not only going to look at this from the standpoint of figuring out the phase and magnitude of the output at a given frequency, but I'm also wanting to sweep it. That is, take your hand on a function generator and run the frequency up and down and see what its frequency response signature looks like. So in that sweep, I'm going to have another analysis magnitude in here called AC analysis magnitude, and I want to make him the same 10 volts, so it kind of plays well. We can make sense out of it. I don't have to do this because it's going to be in decibels anyway, but I'll set that up right now. So there, I'm all set to go, and all I have to do now is wire this. So, setting my cursor on top of the signal source, I'm going to left click, drag up till it's equal, left click, set a corner, connect the resistor. Coming out of R1, go over to our winding resistance, left click, set a corner. Now with this, I could push it up and make a connection, or maybe not make a connection. It's safer to actually physically wire this. And then I'm picking up in this guy node 3, net name 3, which is not going to be useful. Now if you don't have your numbers on your screen displaying the net names, we need to fix that, so let's do that now. We'll go up to Options, Sheet Properties, and under Net Names, click the radio button, Show All. Now mine was set up that way, and yours, if you're on a school computer, may have that option cleared, so you'd have to do it possibly every time you do that. So let us finish the wiring here. I'm going to come from this component over to this ground, and I guess I'll set a corner here, and I pick up a net name there as 0. Why? Ground. Ground is always net 0. Moving him over a little bit and running him up, also have a net name of 0. So anytime you see two net names are the same, they are connected. And that has a lot of advantages if you're dealing with a circuit that, say, has a number of parts in it that have to be fed by a supply voltage. Well, instead of running a whole bunch of wires back and forth, you can just name the nets the same and they're automatically connected. Now we're going to get into analyzing this using virtual and grapher, which is pretty cool. I think I said that, but whatever. So I want to make it so I don't have to remember these numbers. So I'm going to click on the wire, not on the number, on the wire. It's telling me that this is net name 2, and I'm going to assign this a new net name of V out. So I can easily recognize this when I get into that menu. Selecting OK, it's now V out, and likewise for the net number 1, I'm going to name him VN, and there we have our net names named properly. Okay, we're ready to go, so let's measure V out, and we'll start by using a virtual instrument, and that'll be a Tektronix scope. I'm going to set it down at the bottom, click on it, and then I actually see the scope representation. And this is the nice part of this, is you get to interact with the scope as if it were physically in front of you. And this is what a TDS 2024 looks like. So the scopes we have are maybe a little bit different, but it doesn't matter. So that's one of the nice things. So let's see if we can make sense out of this. Here we have 1, 2, 3, 4, which represent channels 1, 2, 3, and 4. External trigger, that would be this guy. Then we have a ground and a probe power, or probe calibrate rather, and we don't have to connect anything. Now, not connecting the ground is okay in multisim. It is not okay in a circuit. The ground is the BNC shell. In a physical circuit, you have to connect this, or your signal is going to be overridden with massive amounts of 60 Hertz from the powering in the room. So that's something you have to remember, is that in simulation you don't need it, and other than that you do. So let us connect channel 1 to this point and channel 2 to this point, and I can just wire that in here. Oops. Here we go, and I'll just go up the side here, or not. Let me try again. Let me squirt my... This is the screen capture window that's floating around. And then V2, let me move him over a little bit. We'll go up to this point. Okay, we're all set. Now, let us turn on the simulation by clicking the Run button. And we can turn on the power here. And what we see is that our VN is very large, and the reason is because our sensitivity on channel 1 is set for 1 volt per centimeter, and our actual voltage is 10 volts. So we need to reduce the sensitivity on this, so I'm going to set this down here at 5 volts. And what I can see here, move this over a little bit, is I'm 2 centimeters, each centimeter is 5 volts. I'm now 10 centimeters peak, so I'm very happy with that. So getting it running again, I'm now going to turn on channel 2. It's also too large, so I'm going to change its sensitivity, and maybe I'll make that 5 volts also, 5 volts per centimeter. Now I can't see this all too well, so what I need to do is come over to the time base and spread things out a little bit. Yeah, that's pretty good. Let me stop it. And I'm only getting half the signal, so I'll click on single. It'll give me a complete shot here. Now what you gotta not do is click on reset, because that'll reset every single thing. Now just taking a look at this circuit is what I see is my yellow waveform, which is our input, is pretty much perfect, 10 volts, and my blue waveform looks to be a little bit over 5 volts. So if I want to, I can pull cursors out to measure that, and let us do that. So I'll click on cursor, and the type I'm going to start with is a voltage cursor. Now notice that the lights are on here next to cursor, which means those are no longer position controls. So I'll start to bring out a cursor here, and I'll bring it up to the bottom of our source voltage, and what I'm seeing here is that the cursor is at negative 10 volts. Perfectly fine. Likewise, I'll bring a cursor here down from the top, and for the heck of it I'll set it on the output waveform. It's just about there, and I see that cursor is at 5.5 volts, which is pretty close to being correct. Now to do a phase measurement, and I would be writing these down if this were part of the lab to use this, is I'll click on this again, and now I'm going to select time. So we can't select phase in this, but if we select time and we know the period, it's a very simple matter of getting phase. So what I'll do is pull this out until I hit crossover on this waveform. Now, the reason I'm using crossover is because the rate of change, that is the slope of a sine wave, is maximum at crossover. It's very easy to set the cursor on that point compared to the top. You can see here that the slope, which would be a tangent to this, well, it's kind of hard to figure out where it exactly is, where with the crossover it's kind of more obvious. Next, I'll look at my other cursor and bring him out and set him at, crossover on the blue waveform. And it would be right there. So, looking at my delta on this, is what I see is that the delta is negative 23 microseconds. And doing a calculation on that, it's negative 23, and I really don't need to worry about the 23, and the reason is it depends on what cursor I put first and second as to whether it's a negative or positive. But what I know from this is my output waveform blue is leading my source voltage, and I'm going to use that information and not worry about the sign of this. So I have 23 microseconds difference, and now I'm going to have to divide that by the period of the waveform. Now the frequency is 500 hertz, and the period, capital T, is 1 over the frequency, and what that gives us is 200 microseconds. So what we look like here as far as the calculation is concerned is 23 microseconds divided by 2 microseconds will give us the ratio. The unit of microseconds divides out. We're going to multiply that by 360 degrees. In doing that, I'm going to do it on a calculator here. 360 times 23 23 divided by 200 gives us an angle of 41.4 degrees. And the actual angle, I'm writing this down, 41.4 degrees, is 48.8 degrees. So why the difference? Well, if we look at the scope, am I exactly on the crossover points? Probably not. It's kind of hard to do here because this guy's pretty little. So let's see if we can come up with a better way of doing this. So what I'm going to do is use Grapher now, and I'm going to get rid of the virtual instrument and click this to make him go away. Oops, I have to stop the interaction first. Now I can delete it. So here's my circuit again, and now to use Grapher, we'll come up to Simulate, Analysis and Simulation. And we want a time-based analysis, and the name of that is Transient. Now we have to do a little figuring. When we start a circuit, we turn it on for the first time. What we have is a startup transient and then a steady state response. And what we want to avoid here is the startup stuff. So I'm going to give that 2 complete cycles to stabilize, and since 1 cycle is equal to 200 microseconds, what I'm going to type up here is 400, and I don't have the option of putting micro in here as a U. It won't let me do it. So I either have to add a leading 0 or enter it with E-6 to represent microseconds. Now suppose I want to look at 1.5 waves cycles of the signal, I'll say, at 200 microseconds per cycle. What I would want to see then at 1.5 would be 300 microseconds. 300 added to 400 allows this to be 700. And again, I have to use E-6 to get microseconds. So that's a little bit more work. Next, maximum time step. What I want to do is set this for 0.6. I'm requesting 10 more calculations per unit in here, which will avoid straight lines. Now for the cool part, we'll go to output. Now, we don't have to worry about numbers. What we want is V out, and we want to contrast that with V in. There's our guy, and all we have to do now is click Run. Here's our waveform. And what I can do now on this guy is to turn black into white. Let me do that. There we go. And I need to make it so you can see this. That will always be a nice thing. Trace width, 4. Trace width, 4. Turn on the grid. What I see in my red waveform, which is the input, is 10 volts. Green waveform, which is the output, is a little bit over 5 volts, and this corresponds very well to what we saw in the virtual instrument. Now let's measure phase. I'm going to turn on the cursors. I'm going to drag one cursor to the crossover on the red. And the same is true with signs on this. Depends which cursor you put where. And the second cursor to the crossover on the green. And now note how much easier it is to pick this up at the crossover. So now I'm going to go take a look at my delta here, and this will be delta x, which is the same as delta t. And this comes at 26.558 microseconds. So let me write that down, 26.558 microseconds. Again, we're going to divide it by the period, which is 200 microseconds, and then we're going to multiply that ratio times 360 degrees. So doing that on a calculator here, 26.558 divided by 200 times 360 degrees gives me a reading of 47.8 degrees. And the theoretical on this is 47.8 degrees. So this came out right on the money. I mean, it was a perfect analysis. And let's just take a look at the peak voltage too while we're in here. So I'm very pleased with the phase, and then I'm just going to take one of my cursors here and move it over to a green peak. Let me get that as close as I can to being right on top of it there. There we go. And what I'm looking at here is cursor number 2, so that's going to be Y2. And what I'm seeing this on V out is 5.39 volts. theoretical on this is 5.387 volts. 5.38, oh, that's perfect also. So as you can see from this, is using graphers, really pretty cool. It allows you a much more granular measurement technique. So that'll do it for that aspect of it. Now let's take a look at the frequency response. So let me close out of this. And as a matter of fact, so I can make sure that people understand this is an inductor, let me do one other thing here. I'm going to place graphics. I want a rectangle. What I'm going to do with this rectangle is put them around the box here. And then for the heck of it, since I'm super conservative, I'm going to put text down. And I'm going to name this inductor. Clicking that, I'm going to drag this right inside the box there, so there's no question about this as being integrated. Remember, the winding resistance and the inductance are integrated together. You cannot segregate them, so node 3 is virtually worthless. Now, let's take a look at the frequency response of this, because we just did a single frequency point analysis, but, well, some instructor might want you to do frequency response calculation, perhaps like me, over 10 different frequencies. So that basically means that you'd have to do everything we did before, and theoretically by hand, you'd have to do it 10 times. So building a spreadsheet in this is very helpful, and using the sweep on this is also very helpful. So to do that, we'll go simulate again, and now I want to go to analysis and simulation, and this time it's going to be AC sweep. So this is my screen, and this is just asking me is where do I want to start and where do I want to stop. Well, for a start frequency, I happen to know that 100 Hertz will be fine, and for a stop frequency, I happen to know that 100 kilohertz would be fine. I need to change this here to kilohertz. And if you get this wrong, is your sweep response is going to be crammed into one side or the other. Then all you got to do is go back and change these. Number of points per decade. Well, I don't know, maybe 1,000 would work. That ought to avoid straight line segments. And then for the output on this, all I have to do is select V out. Don't need V in because it's going to be constant. Well, the voltage source is not going to change with frequency. And now I'm all set up to run this, which I will do here. Okay, this is kind of a bit of a mess. Let me turn black into white. And I want to select this guy and turn him into a trace width of 4 units. And I guess I can do the same with him. It's not going to be around too long. Now this is a rather unusual circuit. And the reason it is because what we have is a resistor in series with the inductor. So we're never going to hit the 90-degree point that we theoretically associate with a true inductor. And we can kind of see that in the phase plot here is where it approaches an inductive component of 90 degrees. It gets up to about 55 and then drops down to be resistive. So I'll explain this again in a minute once we get back into the schematic. But right now what I'd like to do is devote more space to the frequency response. So I'm going to click this and I get this little red arrow over here. And then clicking delete gets rid of the phase response, which gives us more room for the frequency response. Now this is in voltage here and it's displayed logarithmically, and what you can see is that the output here is asymptotically going to approach 10 volts, which is perfectly fine, and in the low side it's going to asymptotically approach 1 volt that you might answer, well, why? So that's something we have to see. But let's look at this in decibels. So I'm going to click this and select Axis Properties, and then select Decibels, Apply, OK. I'm going to use my cursors here, and I'm going to take one and drag it way over here to the right. And what I'm seeing on this cursor, and this cursor is Y2, so that'll be this guy right here, is that this here is a value of 20 decibels, and that would relate to the 10 volts. And the reference on this is not reference to 0. I'd have to do a division to set that up, and maybe I'll do that later. Next, what I want to do is drag the other cursor. We're just going to say that this is 20 dB. I'm going to drag the other cursor until it reads 17. So let me see where I'm going to be here. The other cursor is Y1 and 17. So what I can say about that is that this is 3 dB down from 20. That means one of the critical frequencies in here is going to be just about 8 kilohertz. So that's good to know. And the second critical frequency is going to be, if I drag this all the way down to the other side, and drag this over here, I'm going to be looking now for plus 3. And on my Y2, I'm 3.6. Yeah, it's pretty close right there. And that's going to be at a frequency of 805 hertz. So we have two critical frequencies in this, and this is an interesting filter. It's called a step filter. And if we were to see this, say, in an audio amplifier system, it would be a bass cut circuit, and the cut would be limited to 20 decibels. It couldn't cut any more than that. So that's pretty cool. Let us go back now and take a look at the circuit and see why that is. So I'm going to eliminate this, and analyzing this at high frequencies, well, the X sub L equals 2 pi FL, and as F goes to infinity, the inductive reactance here also goes to infinity, which basically means this part is not in the circuit. In other words, V out equals V in at super high frequencies. Now let's look at the other side of the coin here. If I connect these together, at 0 frequency, basically the inductance, 2 pi FL, F is 0, the inductive reactance is 0, is simply going to be a voltage divider between 450 and 50 volts. So that's going to set the minimum output. So this is why our step filter looks the way it does. So the only other thing we have to explore is to make this relative to 0 dB. So let's see how we're going to do that. Well, okay, let us go back in here, transfer. We'll have to do a little setup here, rather, simulate. And we're coming in here as we did before. Now the only thing we have to do with the output is to remove V out, but normalize it to V in. So the way we would do that would be add expression, selecting V out, copy to expression, divided by V in, and copy to expression, click OK. Now running this again is what we see, and let me get rid of the phase on this also. Again, hit delete, change this into something we can see with 4. Come over here, change the axis properties. Oh, and note that the ratio on this is V out over V in at high frequencies is unity. Because remember, V out equals V in at high frequencies. So I'm going to now set this axis property to decibels. Click OK. Taking one of my cursors here and dragging it, what I see is that this now is normalized. This is cursor number 2 to 0, and this is negative 27 millidB. Let's call it 0. Now I'm going to drag this guy over until I see negative 3 dB. Well, that's pretty close. And this is going to occur at a frequency of 7.89K, which favorably compares to the frequency before. So this is dB relative. Now I'm going to take cursor 1 and drag him way over to here. And that should come in at about negative 19. Okay, negative 19.9. The frequency associated with that's 102 hertz. And now I'm going to take my second cursor, and what I'm going to look for here is 3 dB above that. So that would be negative 17. There we go, negative 17.0, and this occurs at a frequency of 791, which corresponds favorably to the last time we did this with an unreferenced voltage relative to zero. So that should do it. There's a lot here having to do with AC circuits. And with the ability of having this recorded, you can stop and forward and move around and see what you need to do and review, I think, easily. So I'll conclude with this, and thank you for watching.